And we're going to be talking to you guys today about improving vessel efficiency through rudder optimization. So, quick summary of our abstract. Basically, drag created on ship hulls decreases fuel efficiency, causes more fuel burn. The other problem that we were told to look at, or asked to look at by Carnival, was rudder effectiveness at sea. So limiting the amount of induced drag that you have when you make minor rudder deflections to make minor course corrections. And so basically our whole device design was to design a set of experiments that allow you to test, robustly test different rudder designs and then optimize stuff quickly, as opposed to, say, building a ship and then saying, okay, this ship does this, and so. And so basically, tight restrictions on emissions and rising fuel prices. So shipping companies looking for any possible way. So this is just expands larger than Carnival. Any shipping company is looking to save money on fuel. So any small 1 to 2% increase in efficiency they can get, they're willing to take.
So, kind of like Alan said previously, our client was initially Carnival Cruise Lines, and we were supposed to design a rudder to their specifications that would be easily, and that can be easily expanded to a wide variety of ships, large-scale vessels, not just cruise lines. So our goals and objectives for this year, our project in phase 1 was to design an experiment that accurately modeled the effects that the rudder has at sea under turbulence and drag. And that environment can be pretty harsh, so we were trying to design a rudder that would be more efficient at sea.
So, does it go to that right? Yeah, use that PowerPoint thing up there with the laseries there, probably easier for you. Please? No, that one right there.
Just like this. Okay. So for our product specifications, one of the things that we wanted to ensure was that our rudders, regardless of what kind of rudder we used, we wanted to make sure that was the same size. One of the specifications Carnival had for us was they didn't want a rudder that would extend beyond the hull of the ship. So a rudder that would go below essentially like where the hull was. So obviously ensuring a consistent length and size of the rudder just to kind of keep our survey in check. The hull that we used is actually part of the arm fuel hull that's already used in the fluids lab, except it's scaled down to a 1 meter size hull. And so for our propulsion, we used a single 10-volt motor that was directly coupled to the brass propeller, brass 5-blade propeller that we used for our propulsion. Real bit of the standards, so we want basically to look at like two groups here. One is the CFR, and so what part of the CFR says is basically considering our max rudder angles. For our testing, we did 30 degrees, but for most vessels, you're going to be seeing, around 35 to 39 maximum degrees of turning. And then, of course, the DNVGL guidelines. It's Part 3, Chapter 14, Sections 2.2 to 2.5, and that basically concerns the size of the rudder, strength of the rudder, and the forces that are going to be acting on the rudder.
So the project schedule, I'll go over here. So the project schedule, I have here the project from the beginning of last semester. Throughout our work on the project, we've been able to keep very well in line with our projected timeline. Snowvid, whenever that hit, it kind of got in the way a little bit with timing and all that, but we were able to continue, push through, and reach where we are right there. Final report and presentation.
So for our final design, well, let me give you a little backstory about how we approached our designs. So we did a series of batch testing where we changed a single aspect of the rudder, being its profile, its cross-sectional area, different aspect ratios, different geometry ratios, and we kind of boiled down to we want a balanced rudder. And you want a balanced rudder in the sense that you reduce the stress on the steering gear by having the center of pressure located in the center of it. So when you do deflect the rudder, the forces are balanced on each side. And so what we went with was a nested rudder design where we have a large geometric aspect ratio for high maneuverability at slow speeds. So when a vessel's moving slower, it needs a greater surface area to have a reasonable rudder authority. But then as you increase speed, you need less authority, and a smaller surface is adequate to turn the vessel at sea. So that's where the smaller nested rudder comes into play. So when you're out at sea, you use the smaller control surface in the middle to navigate with. Another design to this is it allows the rudder to be positioned forward and in close proximity to the propeller, which allows for better flow across and greater maneuverability at slow speed. So for our design tasks, we kind of broke into two major sections. One being using CFD and SolidWorks to do the modeling, designs, and initial analysis to find performance characteristics. And then we had the empirical testing side, where we did all of our construction of the wave tank, the construction of the model itself via 3D printer, that we then fiberglass and resin for strength and rigidity. And then we're able to compare the results of the CFD testing directly to the empirical testing, which we'll see later on.
So one of the things for this project is our bill of materials was thankfully actually able to be pretty short. A lot of this, for example, our motors, we sourced from the MARR department, and the testing was all done with equipment in the electronics lab. Really all we had to purchase was the PLA that we'd use for 3D printing our actual holes, the resin that we used to put the holes, make them waterproof and more durable. We purchased essentially drain gutters to use as a draining system for the piping, for if there was any water that leaks, it'd go to the gutter and then probably be sent to the drains. And then some epoxy that we used to patch that gutter, as well as any other leaks in the hull.
So for the manufacturing, we use SolidWorks to model the piping system that we desired. And then from there, we made a cut diagram. So we knew we needed 4 pipes, X long, and so on. Then we cut into a bevel on it to ensure a snug fit and adequate gluing, so you don't get scars of glue when you fit the two PVC fittings together. And then we also, for our hull, used a 3D printer, and our hull was modeled in SolidWorks after the Armfield vessel from Naval Architecture that we were then able to use the table of offsets for. Because the table of offsets, if you boil it down to its simplest form, is a series of X and Y coordinates that are spaced out in the Z direction at a specific distance given by the table. And that's how we were able to recreate the model into SolidWorks. From there, we printed it, we sliced it into 5 sections to allow the printer to print it. It stands a meter tall. And then from there, we sanded it, the plastic down, put down a layer of fiberglass, and then put 4 layers of resin onto the vessel.
So for our unit testing, we tested the VFD, we tested the wave tank, the rudders, the 3D hull model, and the DC motors. For the VFD, we found that we could set the pump. Our scaled down version of at sea speeds, we decided would be 4 feet per second through the VFD. We tested it to that. It worked to 4 feet per second. It applied that. For the DC motors, we used the voltage supplies in the electronics lab to take the motors that the school provided. We tested them by applying voltage until they would rotate, and then backing voltage down before they stop and then bringing it back up to 9 volts. The rudders and the whole test its most of it work at seat conditions in the water, the whole making sure that it doesn't leak, that we can weigh it down in the water, get the draft right, and the wave tank, after completing the assembly, putting all the pipes together, putting water in, making sure that it's watertight, or as watertight as we could. For integration testing, we assembled the test tank, the VFD, and the test gauges. We were able to test the wave gauges through this means by applying the 4 feet per second from the VFD through the wave tank, and thus getting results from the wave gauges. We also assembled the testing apparatus of the model by attaching the rudders to it, mounting a motor onto the propeller, and making sure that it all works together, it's watertight, and that we can continue to test through it. This is our dye test. One of the data collection tests we did, we put dye in the water just before the vessel as the VFD was flowing 4 feet with the pump. What we were able to see is that the dye affected the rudder or the ship the same way that the CFD model and software showed. We did this without motorizing the propeller and with motorizing the propeller, and the results matched along with CFD software. Other data collection tests we did were for the rudder efficiency, where we would take the baseline spade rudder that we had, compare its efficiencies with that of the nested rudder, and we did this also with and without a motor. With the motor, we set it to 75 RPM.
So, probably wondering why there's a bulbous bow, noise-canceling headphones, and stern of an ocean liner on the slide. All 3 of these operate on the same principle, constructive and destructive wave interference. And so, back in the day, when you wanted the ship to go faster, you could either apply more horsepower or make the hull more efficient. So it wasn't so much a sense of I need to save fuel as I want to make the ship go faster. Nowadays, it's kind of a happy side effect. Is I can run the engine less hard, not as hard, and still reduce fuel burn. But basically, wave drag on the hull can be reduced in a number of ways. Ships today are actually being slowed down past the point where the bulbous bow is effective anymore. So they're actually just adding drag. So a lot of very new build ships right now are being built without bulbous bows or very, very small ones. And then basically the effectiveness of the bulbous bow being reduced. And so in addition to the stern design and the transom design, it can also affect your wake. And then the wake is actually causing drag on the ship. So if you can reduce the wave height and the period of the waves are acting on the hull, you can actually reduce drag that's acting on the hull.
So for our test development, we went with our baseline spade rudder. This was just since we weren't able to get the actual specifications from Carnival Cruise Line on either their hull or their rudder, we had to get creative, and that's where we came to the conclusion to use the Armfield model. And from there, we looked and researched what hull shapes are consistently used in a cargo vessel like the Armfield. And we came up with the baseline rudder that we used to compare all of our data to. And then we induced the same test for the baseline as well as the nested rudder. And we compared it to all of our designs that we went through, but we finished and concluded that the nested rudder was the best choice, and it moved on to actual empirical testing. All of our rudders went through CFD analysis as a standalone rudder without hull interaction, and then went through another analysis with the hull interaction to see performance, location, and give us a primitive idea of how the rudder itself would perform. And it outshined all the others by a good margin. So that's why we went ahead and selected the nested rudder.
But can you just go back one? I know we got the questions on that, but so I don't need to go back later. Can you explain exactly what you see on these graphs there? Because I understand some of it, but there are people here that doesn't.
So what we see here is the drawing of the rudders, baseline, nested, and then what we see here is a flow tracing of the different pressure gradients as it flows through, flows across the rudder.
So the blue you see in the middle, that's the rudder itself, right?
The rudder is the gray portion in
Yes,
the middle,
okay.
and then the blue here is a lower pressure, is the lowest pressure. Green is the next step up, followed by yellow, and we don't see any red except for orange over here, and that's just the increase in pressure gradient.
Okay. I just want to understand.
So basically what we measured was the other group measured actually force that the rudder applied. We actually measured wave height coming off the stern. So we basically were measuring the wave using 2 wave gauges, which are very accurate. You can measure down to 5 centimeters or less than 5 centimeters, and then I took a data point every millisecond. So measuring over a half second, we had 500 data points. And so basically what we found out was that doing both our tests with the propeller, we found out that the standard rudder with the propeller, because it sits further back from the propeller, you actually get a higher induced wave on the opposite direction of the rotation of the propeller. Because as you'll see in a couple of the videos we have underwater, you'll see that the propeller actually induces a pressure wave, a negative on the downside, and an upwelling on the upside of the propeller. And this whole pressure wave moves back as the water is moving across the rudder. But on average, going back between the nested rudder and the standard spade rudder, we saw an overall lower wave height and shorter period between waves that was small. Yes.
Jake, will you share the screen? That on Zoom?
Hope so.
Oh, I don't think so.
Oh, yeah, well, that's...
There we go. Restart. Thank you.
Should we restart?
No, no. Just keep going.
Okay. It's okay, this is the important part. So what we noticed was an overall decrease in wave height on the stern of the vessel with our tests that we did. So yeah, like I said, Q3 overall average, or Q3 2-3% decrease in overall average height at the stern of the vessel from baseline to the test case, and then a 5 to 10% decrease in wave height end period with the nested rudder at full deflection. That was with the small center nested section turning. Because it's such a small section, the wave that it actually induces on the stern was minimal. But you still have the requisite steering effect to maneuver the vessel at speed. And then also by saying the propeller turbulence was made partially laminar, you can see in that right video, was made partially laminar by the longer chord line. It's still obviously very turbulent, but that longer chord line and the fact that it's close to the propeller really kind of smoothed out a lot of the water that's coming across the back of the stern or back of the vessel. Go to the next slide, please.
So what we see on the back is just a holding in position. Is that what it is? Or is it strain gauge?
The 2 gauges are keeping it straight, and then we're measuring waves that are coming off the stern.
Okay.
So we just wanted to briefly show you guys probably the most visual effects that you can see in our comparison between the SolidWorks CFD. As you see, the lines start to curve upwards to the upper side of the image, as well as the die. This is both the 30 degrees deflection to port, and you can see how the die is starting to deflect out this way, as well as the CFD indicating the same kind of flow. So that's one of the comparisons we were able to make back to our CFD analysis via the flow tracing. Again, the different pressures of flow through the system.
So basically, kind of a summary of our results. Reduction in wake eddy times can be reduced by adjusting basically these design factors. So transfer design and propeller speed design, that's down to vessel specifications and need. But however, the rudder dimensions, so forward length profile and height, are all things you can change fairly easily and then replace rudders on ships. So part of the original design requirement, which isn't really kind of including more, would kind of still apply here. And so basically what we ended up making was a rudder that you could adjust the dimensions of without having the negative effect of induced drag at high speeds by deflecting the rudder. So because you have this center trim tab that's able to deflect at vessels at high speed, you can have a longer rudder that you don't have to deflect at all while you're moving at speed. And so then that allows you to adjust the efficiency of the rudder.
So I'm going to talk a little bit about our risk assessment throughout the year. So we were working a lot with water and electricity. I know we had plugs hanging above the wave tank, the test bed. So that was definitely a concern. A leaking hole. As the previous group said, leaks were crucial this year. We did have a few leaks, but we were able to patch those up on the hole. The flow tank, we weren't as lucky. That's one we couldn't really mitigate as well as the other one. We were able to slow it down, but there's still a few leaks, but we put a gutter under it and we're okay. It doesn't affect flow. An electrical fire. This one, we wanted to ensure that our breaker box was clear of any tools locked up near it or anything obscuring it. And then our last risk was tank overpressure. We wanted to ensure that our manual is read thoroughly prior to using the VFD. We wanted to make sure we didn't miss any steps or miss any instructions that we had to do. And that's basically our risk for this semester.
So I was part of the flow tank design and assembly, and then also kind of in charge of physical rudder testing and data analysis.
I did the rudder design, all the CFD modeling for the wave tank, the hull, and rudders, and then as well as the data acquisition of both CFD and empirical testing, as well as tank type dimensions, as well as assembling the wave tank.
And I did a lot of weekly scribe, a lot of weekly assignments, and I also aided in assembly.
I aided in preparing piping to be installed and assembling the tank and helping out with testing as I can.
And so for me, I basically made sure that all the motors that we procured from the Marine Department were all both able to be operated, and that also the performance characteristics of the motors that we choose were pretty well, we're in good tolerance with each other, so that way if we had to switch one out, we wouldn't have a large discrepancy in our testing. I also did help once the wave tank was assembled and all the issues with the leaking, I did a lot of work trying to minimize those. And then for the rudder testing, one of the things with the VFD and pump operation was that when you kind of leave those kinds of stuff to the collective, a lot of times the necessary procedures and the precautions you have to take both in starting it up and securing it, people would kind of get caught up in other things ignored. So I took that on my own eventually just to ensure good operation.
So moving forward and kind of our conclusion here. So we were phase one of a much larger project that's out of the scope of this class. But phase two of this project is taking the information that we learned and applying it to vessel specifics, and then actually looking at the effect that it would have on specific fuel oil consumption over a given period of time, as compared to, like, say, a baseline that had like vessel of the same class. Yeah, that's it. Question? Yes.
If it hadn't have been for the screen, it would have been a margin on this.
Johnny, where are we at?
We're at 1250.
Well, see, that's your,
So this is our
that's your
test.
safety margin analysis there.
This is our 4 feet per second test speed.
Okay.
Without and then so obviously for the actual test we
So we had two test conditions. We tested it in two conditions. One with the propeller and one without the propeller. So we wanted to induce the turbulence, and then we also wanted to measure it without the introduction of the propeller.
Some other special effect, and it only happens every so often, is it because just the waves
Yeah.
going through? Oh, is that right?
See how every so often you get like a little bubble flash?
So a vortice is
Yeah.
introduced and air is cavitating through the propeller.
Drop your water line just a little bit.
So we interject the dye right at the base of the hull and allow the propeller to start to suck. And you can start to see the eddies forming around it. And if you notice how the suction upward and the mass, a lot of the dye is flowing about the middle of the rudder.
Yeah.
That is something we also saw and verified with our CFD test.
Oh, is that right?
So it's some,
So it wants to go towards the middle.
Yeah.
More so, that's pretty good.
That's the benefit of moving the rudder close to the propeller, because the propeller doesn't have time to spin that water all the way out to its like diameter.
And being a longer chord line, it allows it to relaminate across the rudder.
Okay.
Off.
Mm-hmm.
And this is in the high maneuverability case.
So you got a big wave right here. Is that what you would expect?
Yep.
Okay.
And
Because
so
he's trying to go this way.
he's trying to make the turn. So we'll interject the dye, and you'll start to see from the top how it's deflecting out to the right.
Yeah, and he's hitting more the top of the rudder now
Yes.
than the center. You want to try right here? You can get that angle, maybe. There you go.
Can we get another pipette full? The inner rudder deflected, and we're at our cruise speed of about 20 so knots.
So
4 feet a second for the model, or 4 feet a second for the model.
yeah. So let me ask this. So 20 knots. Now, would you do this only in port to do the inner rudder, or would you
No,
do it
the
at sea?
larger rudder with the high.
Oh, the larger rudder in
high
port,
surface
so you get the
allowance,
big surface
so you
area.
get
Okay.
a lot of maneuverability.
Now you're just doing the little course corrections at sea.
Yes.
Oh, okay. Now I'm with you. Okay. I'm slow.
So I'll
Get
just
there.
spin it up,
Gotcha.
and we'll start to see that we do get a good amount of flow being deflected across that inner rudder, which at sea you only need a couple of degrees at a time.
So is it splitting pretty evenly? I see a pretty good amount of dye on this side.
Well, that's that pressure differential.
Mhm.
That's what's gonna be your.
That's the push to make
That's
it
the
whatever.
push that makes the turn.
Interesting.
That's why it sucks to the.